Good evening, everybody. Let's get started. For today, again, as a note, this session is already recorded. It's being recorded on the Zoom and also
Good
being.
evening, everybody. Let's get started.
Why?
For today,
Who is
again,
reflecting?
as a note.
Okay, here it go. Sorry for that. And also being live telecast to the YouTube. For the reason one or two students don't have Canvas set up yet, I guess. I hope from next week, we don't need to do the live telecast on YouTube. Okay, and also focus mode is on. That means only I can see your videos. No other student can see or no one else can see your videos. Okay, saying that, what were we? Like today, is the next phase of our discussion on the computing hardware system. And this more like studying the main components in a computing system. And the functionality we already have seen in last day's session, that how a simple program like C equal to A plus B works inside a computing system. And today, we are more discussion on to deep into each of the component of it, and also we'll get introduced to the clock system in this topic. And I hopefully you guys have already studied from the pre-recorded lectures and notes. Let's see. Okay, so as usual, let me start with the poll saying that, hey, where are we? So let me launch this poll. Please answer. You may answer it anonymously, but yeah, mark it truthfully what we have done today. In the meantime, let me set up. I want to do this. Okay. "92 of 97 has participated. Waiting for 4 more students, maybe 10 more seconds. Okay, let me share my result with you. All of them, like, have you watched your lecture videos and read lecture note for today's topic? 46% of you said all of them, and 50% said some of them. So 96% is kind of reviewed somewhat. Though all of them actually went down, I believe last time I saw more than 50% of you did that. It is going down, but keep an eye, right? Please make sure you review the topic before coming to the class. Have you noted your queries in corresponding discussion page? For 7% says yes, 18% said no. I don't have questions, 74%. That's worrisome. If you don't have question, that means either of two things. Either you have understood everything or you have understood nothing. The first point is obvious, like, I don't believe you have understood everything, especially given that completely brand new subject like hardware. So yeah, you probably by default take it that you haven't understood anything. So please make sure you go through the topic once again till you have some question raised in your mind. Okay. Okay, all right. So let's do these things in a little bit different way. So major part of that understanding of this lecture is mostly around how the memory works, like how it interacts with the rest of the system. That is one complicated stuff. So let's try to understand that operation with some example. Okay, let me share my screen. Okay, and Okay, so if you open up your computing system and make a very simplified view of it, you have basically one processor, something. I just happened to grab a picture from internet of MIPS, that what we'll be studying, and a memory card. I just randomly picked up another picture. But what happens between them on the motherboard side, if you open up, you'll see it like there are a lot of electrical pins coming out from the processor, and there are a lot of pins, electrical pins, connector pins on the memory card side. And if you look at the motherboard, you'll find, in fact, all the pins are connected with each other, right? These two components, all of them. These are physical wire we're talking of. And in computing system, each such wire actually represent one bit value. If there is a presence of current, it's 1. If there is absence of current, it's 0. Or presence of voltage, 1, logical 1. Absence of voltage, logical 0. That's how it works. Okay. So each physical wire, physical line, electrical line represents one single bit in a computing system. And we draw it nicely in a schematic diagram, like with the boxes and everything. Carefully mark the pin as a names, like to reflect what the purpose of the pin. For example, here, this set of pins, get it right? Oh yeah. Okay. This group of pins start with ADDR, kind of trying to say, hey, these are the address. See, these are the address pin of the processor side, and this is like this group of pins are data pins, and they're indexed. Okay, so they're kind of grouped together. The purpose of this is to convey, like send out or take in the data inside that electronic component. And we have two signals, read and write, onto that system. And if you look at the memory, memory also has corresponding pins, address, data, read, and write. Okay. So now, if we want to make that connection of the previous page like this, like electrical line connected from one each other in the schematic view, we draw them. We draw simple lines, right? Simple lines connecting, telling that, hey, address 31, that pin is connected to the address 31 of memory, and address 30 connected to the address 30, and so on and so forth. Similar for the data. Data 31 connected to the data 31 of the memory. Data 30 of the MIPS or processor side is connected to the data 30, and so on and so forth. And this line represent that, each of these line actually represent that physical wire, like you see on the motherboard, that one pin connected to another with a physical electrical wire. So they represented one electrical wire. And now, so we are now talking about how many lines we are drawing here. We are talking about 32 plus 32 plus 2, right? 66. Instead of drawing too many lines, we can simplify this diagram like this. This is a group of, this is an address, this is data, and we draw a line and kind of mark it slash. This is the marking of the, like, this is a group of signal, not an individual signal. This is a group of wires, and there are 32 of them in that group. Data, similar thing, a group of wire, and it has 32 of them. And together, they represent the value of address and the value of data. And this multi-bit, this is a multi-bit connection in the schematic diagram. We also call it like a bus. It's an address bus and it's a data bus. So bus is nothing but multiple bits connected to, like, not connected, like they group together for a common purpose. So here the address bus, the purpose is to communicate the address value from the processor to the memory. And data bus, its purpose is to communicate the data between processor and the memory. Either processor sends the data to the memory for writing, or memory sends the data back to the processor for whenever there is a read request from the processor. The other two, read and write, they're the control signals, and they're not a bus, they're single wire. Like this is a single bit wire or single bit signal, which carries either 0 or 1 signal from one to another. And in the sense that these things, except for the data, this address, read and write unidirectional. They originated in the processor, goes terminated in the memory. So only processor can produce a address value, produce this control signal, which is sent to the memory. Not the other way. Memory is a passive device in that sense. It does not control anything. But processor is an active device which controls operations and interaction between these two. Okay. Data is, on the other hand, bidirectional. Means either processor can send some value through the data bus to the memory, or memory can send some data back to the processor through the same set of electrical line. Okay, that's very important concept. So it is the same set of electrical line. Data goes either from the processor to the memory or from memory to the processor. So take a note on that. And of course, last but not the least, its operation is synchronized with a clock. Okay, this clock is like in this scenario, we are feeding the same clock signals to both microprocessor and memory. Now let's look at some operation. Okay, before going to that, is there any question? Please raise your hand and then speak up as if I tell you.
So this is review, but the clock is external to both the processor and the memory. Is that right? It's external.
Yes.
Like okay.
Yes, this is external. Yes. Okay. Okay. All right. Now next. Now we draw something called a timing diagram. So what is a timing diagram? In a sense, it's give you a temporal sense of what is happening in each of the signal in this system, like these wires. What is happening in the wire? Temporal means on the time scale, like this time which has what value, that time which has what value. It simply depicts that sequence of phenomena over these different signals. So we have put these 5 different signals onto our timeline. Let's say we started at timeline 0, and we have clock, read, write, address, and data. We'll see what are the different values at different point of time. Let's say at the time 1, T1, microprocessor wants to write 15 at address 12. What it will do essentially, at this point, which is defined at this time point T1, is defined by this clock ticking up. This means it was at logic 0, now it went to logic 1. The clock signal was logic 0, it was logic 1. No one controls that. It is just an universal phenomenon that clock keeps on ticking. Okay, so at this time point, clock ticked from 0 to 1. At that point, processor makes the read signal 0. So we are keeping this signal at the same level. This is, let's assume this is representing the logical 0 level. And it makes the write signal 1. So write signal goes up to the logic 1 at that point. And also we are representing in this diagram 0 as red and 1 as green. Okay, just take a note of that. And what happened to the address? Now processor wants to write 15 to the address 12. So it must send the value 12 on the address bus. So I'm representing that as a blue because it is like combination of red and green. Like some bits will be 0, some bits will be 1, which combination of this 32-bit will represent the value 12. And these things will basically how these values are represented with the binary values with the bits will study it in the next lecture. Lecture 3 is all about that, like how we represent the values in terms of binaries or bits. Okay, but just assume that some bits become 0, some bits become 1, and that combination is representing 12, and that is being sent to the memory. So we said that. The processor also need to send the data. 15 also, some bit is 0, some bits are 1, and that represent the value 15 and being sent to the memory. Look at the arrow of this information. It's coming from microprocessor going to the memory. Okay, that happened at the T1. Now T2 clock signal goes down. In the digital system, mostly nothing happens in the lower transition. When clock signal goes from 1 to 0, nothing interesting happens at that point. Then at T3, this operation is done in the memory. So memory writes 15 at address 12. So this whole cycle, this one clock cycle from one positive edge, this is going from 0 to 1 positive edge to another positive edge. It's a one cycle, and that, let's assume for this device, memory device, it takes one complete clock cycle to write the data into the given address. And let's call it a write cycle. So this is the first write cycle 1. And at T3, microprocessor wants to write 41 at address 29. So it will do the same order. It will keep the read at 0, write at 1, and issue and 29 value on the address, data 41 on the data bus. T4, it is a positive negative edge of the clock. Nothing interesting happens. Next positive edge, which completes the write cycle 1, at that point, your data 41 is written in the 29. And also processor at this point, let's say it wants to read from address 12. So what it will do, it will make the read signal to value 1 and write signal to value 0. That's exactly depicted in this timing diagram. At this T5, read signal goes to logic 1, write signals goes down to logic 0, and address bus is set to 12. Now, what happened to the data bus? Right? Nothing. Data bus, I see there, I just depicted as a black line, means no activities are there, or at least we don't care what is in the data bus. Okay, not important. So we represent that in a timing diagram as a dashed line. Okay, dashed line, that I don't care about the values. There can be something, it is not important, it is not part of the function of this whole system. We represent as a dash. So T6, nothing interesting happens. T7, next clock cycle, what happens? Your memory completes the read operation and sends the data back, like we are reading from 12, right? So this read sends the data out on the data bus at T7 from memory towards the processor. So this 15 is being sent here, okay? Now, next cycle, nothing interesting happened. Next cycle, this 15 is consumed within the microprocessor, okay? So T7 cycle, your data is presented from memory towards the microprocessor, and by T9, microprocessor is done with doing whatever it wants to do with that data. And at the same time, microprocessor wants to read from 12, right? Address 12. So what it will do the same thing, keep the read to 1, write to 0, issue and value 12 here, but this 41 is not coming from processor to memory. It is the other way, right? It is for this read at 29. That read value, memory is presenting that read operation result at T9 on the data bus. So it is coming from here to there. So that means you see the read cycle is longer than your write cycle. Write cycle ends right there. But read cycle, since it involves memory and also involves processor to consume the data, it is longer. And let's say in this case, it is one cycle. Like let's say this processor needs one cycle to consume the data. So next, T10, nothing interesting happens. And T11, that data being consumed into the microprocessor, right? So your read cycle 2 is this from T7 to T11. Your read cycle 1 is from T5 to T8. So see, the read cycle kind of can overlap. Back-to-back read cycle can overlap with each other, okay? Now, let's say at this point, processor wants to write 48 at address 25. It can issue 25 on the address line, fine. Now what it need to do? It need to send the data 48 onto the memory, right? So it needs to send that, but wait a minute. This same line is being used by the memory to send the data 15 back to the processor. Everyone agrees with that at this situation? So that's a, oh, I cannot do that. Hey, they're same set of wire, right? This is just that same set of 32 wire, which is being used by memory to send the data back to the processor. How come processor can send data 48 to the memory at the same time? It cannot simply do that because that is the same resource. That data line cannot be used simultaneously by two entities, right? So that is the cause of the problem, that at this time point, processor cannot possibly send a write request. What it need to do instead, let that read cycle complete, okay? Read cycle 3 completes at T13, then issue your write operation, 25. Now, at this T13 point, your data is free, data line is free at this point. If we look at that, this point is still being consumed, and at that point, the data line is free. So microprocessor sets the read value to 0, write value to 1. That is a write operation request to the memory, sends the address, sends the data at the same time, and write cycle is done there. So you mean that T11 is a no operation, because we want to do a back-to-back read-write operation, a write operation immediately after a read. But that's not possible because at that point, this data bus was being used by the memory to send data back to the microprocessor. That's why microprocessor needs to wait for a cycle and consume that data before it can start a write cycle. Question? Yes, Ong.
Wait, so if you happen to do like right after, while the read cycle is still going on, will there be like a processor failure or like some sort of machine failure that goes on, or will it just not respond to it?
So microprocessor won't dare to do it. Simply, let's put it in that way. Okay, no one is, it cannot be done logically. Yes. Anhad Sran. Did I say your name correctly? Anhad. How do you say your name, please?
It's Anhad.
Anhad.
Yeah.
Okay, Anhad, please go ahead.
Professor, I wanted to ask if, like, why does it take such a long read cycle for microprocessor to process data?
Come again, sorry, I couldn't hear your voice clearly.
Why is read cycle so much longer than the write cycle?
Because read cycle, what we're defining here as it's a, from memory point of view, your read cycle is one clock cycle, right? Memory done. Memory is got a request and catered that request. Now, at this point, this data has to be consumed by the microprocessor. So now T7 point, for example, now microprocessor is involved, get the data and do something with it till T9. So two entities are involved here, right? Sequentially. So that's why it is taking a longer cycle if we want to make it a complete cycle of coming from the requesting the read operation and consuming the data. That comprise the whole operation of the read. Whereas write cycle, it's a request and the operation is done. There is nothing, no other entity involved. It's only the memory. Processor sends a request at T1, and by one clock cycle, memory ensures that that data being stored inside it. And that's it. That's the end of the story. So that's why it is like from system, like whole microprocessor memory combined system, your write cycle is smaller because it involves one entity versus read cycle is longer because it needs both party to complete this operation. Okay. Any other question? Yes, Henry.
So I realize that this is an idealized system, but wouldn't it be better if the memory was on the falling cycle? Because it would take time for the processor to realize that the clock has changed, and then the time delay in changing the signal. Because if they both act at the same time, there could be bad data on the line, wouldn't there?
That's where the synchronization process happens, but you have a very interesting point, like what you are proposing. What if like processor acts on the negative edge and memory acts on the positive edge? Is that your point?
Yeah, or the other way around, doesn't matter.
Right. So some advanced system has tried it, and in fact, some of the system has deployed at least at the subsystem level this kind of synchronization with half clock cycle operations. The cost here is the circuitry would be complex, right? Logically, it makes sense to do that, but to make the real circuit to operate on the falling clock cycle and synchronization between positive edge and negative edge clock phenomena would require additional hardware circuitry, and which essentially would slow down the operation. So basically what I'm saying, there is a cost analysis, benefit analysis for that configuration that what you are proposing.
Okay. And so would both the processor and memory wait for a little bit then after the rising edge?
So, okay, this is the ideal diagram, right?
Yeah.
It's up and down, but that rise time and fall time are all considered in the design.
Okay.
Okay, so that we can actually kind of infer, okay, they are the ideal signal, and whatever behavior we're looking at in the real life also same behavior would happen.
Okay. Thank you.
Okay.
Oh, wait, I had a question.
Yes, who is it?
This is Vedant.
Vedant. Okay, how can how don't I don't see you somewhere? Where are you? Let me see. How can I find you? Vedant. Can you raise your hand, please? Let me see if it comes to me. Is anyone? Probably your video is not on, right, Vedant?
Yeah.
Your video is not on. Yeah. Yeah, you don't need to, but okay. It's good to always see some name and face when you're asking question. Yeah. Thank you, Vedant. Yes, please.
Yeah, I had a question. So, what happens like if the memory is like extremely slow?
So in that case, your microprocessor needs to take account of what kind of memory you are attaching to, right? So, and that's, I would say, let's put it in this way. When a computing system is designed, all those factors are predetermined. You cannot just plug in, play, randomly take a component and plug it into a system. It won't work. It is already predefined that what kind of memory can be used with what kind of microprocessor. And that way microprocessor kind of guaranteed that these operations are all viable to each other. So let's say someone is like building up some computer with a slow memory and microprocessor, right? The microprocessor need to support that slow memory device in a sense, okay? But also just take a note, what we are discussing here is a very simplistic story about the system, so that we kind of understand the very basic, very simple system operations. Modern computer has very complicated situation, especially with multiple hierarchies of memories. Like it has cache memory and different level of cache memory, level 1, level 2 cache memory, which actually resides inside the processor. And then it comes to your system memory, which is the memory card I have shown. So the interaction doesn't directly happen between the microprocessor and the memory directly. It happens between cache to the main memory. And there, what happens, that completely different story. Basically, all the data transfer happens as a block, as a chunk data between them, okay? And only the processor is communicating with the cache memory, which is a part of the processor itself. It resides in the processor, and they operate on the same clock. And there, no synchronization problem happens at all. And that's how you can possibly take care of possibly use different type of memories. You can put different type of memory cards onto your system still works, because of the fact they exchange data as a bulk. And it is not only on the clock, there are additional signal involved which indicate, hey, did I complete my operation? Am I ready to get another request? Lot of complicated protocols goes into those areas, those communication. Okay, so it's not a network protocol as far as I say, but there are protocols like AMBA or DDS, etc. Those kind of typical protocol comes in where control has more signals in it. Status signal and ready signal, acknowledge signal, and things are complicated in the real situation. Okay, so take this as a very simplified model to understand what goes on when you write a program and what goes on in a computing world. Okay.
Yeah, thank you, Professor.
No problem, Vedant. Yes, Ilyas.
Yeah, there was a question that in the chat that said, are the clock system, I think they're talking about the general sort of the system clock and the internal memory clock speed the same?
Internal memory clock speed are same. Yeah, they operate on the same system. Okay, is that question?
I think so, yeah. It's a little vague, but it says, yeah, are the clock system speed and the internal memory speed the same? So you said they're the same.
Yeah, internal memory has to be on the same speed. Like if you're looking at the cache memories, they have to be on the same speed with the processor. Yeah, of course, like it is not absolute, like all the different processor can deploy different strategy. And from hardware engineering point of view, what I can say, it is always possible to build up a different speed component. Like it's a matter of how you synchronize the operation between them. But more difference you want to make, more flexible you want to make, your hardware circuitry gets more complicated. Yeah, so modern processor may have some component which operates in a different speed, but they have these problem to solve of synchronization of the operations. And when someone architect that kind of system, they always go with that return on investment kind of study. Hey, if I want to do this complicated circuit, will it really benefit my performance? So everything comes down to the performance at the end of the day. Okay.
Thanks.
Anything else? If not, then we can take 5-minute break now.
I have a question actually.
Yes, Raymond.
So just to clarify, the microprocessor, when it reads, the memory doesn't do anything. Like the microprocessor does most of the work, or all of the work.
Yeah. As I said, memory is more like a passive device. It's just get some request and scatter that request.
Okay, cool. Thank you.
Microprocessor who actually do all the work. Okay. All right, let's take 5-minute break and we'll be back after that and we'll go through the slides of today's lecture. Okay, let's get back from our break now. And let's look at the slides and let me know if you have further question on these topics. So what are we learning in this lecture? We start with an arithmetic and logic unit, ALU, and we kind of saw what's the functionality of the ALU. Oh, I didn't share yet. Okay, here it goes. Functionality of the ALU and how to draw a simple ALU in the sense of the schematic diagram or interface diagram. So we started with the concept of the software APIs. We all used software libraries, right? And some standard function we use like a println, like scanf, that kind of thing, right? And we never wonder what inside those function, library function, how the println has been implemented or the scanf has been implemented. We never wondered that, right? We just use it. Well, all we need to know what parameters we need to pass, right? And some parameters can be of passing by values, some parameter can be passing by references, and so on and so forth. So all we care about the interface, and that's part of your header files of the libraries, right? Software libraries. Similarly, interface diagram, you can say that this is analogous to your function or method footprint that goes in your header library. All it says, okay, these are my input, these are my output, and this is what I do. How I do inside, no one cares, right? It's kind of a black box. It's only who design the ALU, who implement the ALU electronic circuit and all this stuff, they only care what goes inside it. It's almost like if you open up the println implementation in the library, you'll find out like what it does, what exact step it do, right? Similarly, in the ALU implementation software-wise, library-wise, it does something like very similar to this. You look at the operation code and just perform that operation. Okay, very, very top level. So these are software implementation. On the hardware side also, it do the similar conceptual thing. It tests this operation code. If it is addition, it do this bitwise addition. If it is subtraction, it do bitwise subtraction, and so on and so forth. How it does it at this point, don't worry about that. We will learn eventually at the second half after the midterm, we'll learn how ALU actually compute your addition result or subtraction result. Let's say if you ask it to multiply 5 multiplied by 10, how it comes up with 50. We'll talk about that, how the real implementation in the electronic or hardware, logical world it does. But this is not the point. This point is that, hey, there is an electronic component which does this, and its interface looks like this. And ALU has a special note. It is loved by hardware community so much, it has been given a special symbol. You don't need to remember it. You can just draw a rectangle block and mark it as ALU. That's sufficient. But if you draw this, you don't need to write it down as ALU. Everyone knows this is ALU we're talking about. Okay, so that's one standard thing there. Okay, now next, what we talked about clock system model. We talked about why clock system is necessary. In a nutshell, even one ALU, like when you are operating an ALU, same ALU electronic circuit in a different environmental condition, like high temperature, low temperature, high humidity, low humidity, when the result comes up, actually can varies with the environment itself. Okay, environment can slow down or speed up operation of electronic circuits. So on the timing diagram, so far what we were assuming, hey, this result as it comes instantaneously. We present operands, we present operation code, boom, it just produces a result. But if we actually look at like minutely at the timeline, it doesn't operate like that. Like let's say T1, at this timeline, we set up these values, operation 1, 2, and like operand 1 and 2 and operation code. Your ALU result doesn't come at T1, but it can come at some later point of time, maybe like at TA, or depending on, let's say it is a faster ALU, it might come at TB earlier. Or even like if it is a summer day, it can come faster. If it is a winter day, it can come slower, so on and so forth, right? So we don't know exactly when that result would arrive. But it is very important to know whoever is asking for that operation to know when I can probe for the result. Because if your result comes after TA time, but if you probe for the result before that, you are getting a wrong result. You have to probe for the result after TA for that result to be valid. Or TB in this faster ALU, you can probe after TB, that timeline, to get the valid result. Otherwise, you'll be wrong. So how do we synchronize like whoever is asking for a result and what the ALU does? So very simple method is to establish a timeline treaty with it, right? Just tell that, hey, I am producing it at T1 and I will go and probe it at T2. Make sure your result comes by that time. It doesn't really matter when it comes, but it matters that at T2 time, if I probe result this port, I get the result out. That is the pact between ALU and the rest of the world. And that's where your timeline concept is very important, that it is telling that, okay, at T1, I am going to submit my request. T2, that is your deadline. By that time, you produce the result. So this time concept comes in now. Now, how do we represent time in hardware, right? In human, we know that, okay, there is a concept of time somewhat. That's also a mystery, how humans perceive the time. But in the non-living world, like electronics world, how do we do it? Okay, so that's the reason we went for a component, electronic component, which repeatedly sends a signal out periodically with a constant time period. So it basically, though in the previous session, what I have shown you the clock as a very squarey waveform, like it goes up instantaneously and goes down instantaneously. But in fact, from 0 to 1, it takes some time to, like flight time, up flight time, down flight time. It takes some definite amount of time. It is very small, but it is there. So this is called a rise transition time. And this trapezoid, this part is called a falling transition time. Means it is rising from 0 to 1, stay there for some time, and go down to 0. And if we probe a time value between midpoint of this trapezoid, that is a time high by definition, and other part, midpoint if we probe, that is called a time low. Like how much time it stayed high, how much time it stayed low. And this signal is very periodic, it is constant. This is the only constant in the whole computing system, your clock period. And every other system component, say it a memory, say it ALU, say it a register file, say it controller, all bound to these ticks. It does operation at these ticks at the certain point of time. And that's why the operation can be synchronized with each other. Okay. And in this slide, we talked about some of the definition, some of the, as I said, there is a rising time, falling time, time high, time low, etc., etc. And there is another definition called the duty cycle, which basically tell you that how much ratio it stayed to the high signal in the entire clock period. And we also talked about the clock period definition. Did we talk about that? Oh, here. Okay. We talked about the definition of clock period, which is, but why don't we see the formula anywhere? Maybe it's in the note. Okay, so is a time period is a hertz or gigahertz or megahertz, that kind of thing. It talks about, and your formula to compute from frequency to the time period is time period equals 1 by f. It does come from the physics, time period, like time cycle definition. So your frequency, for example, is 1 gigahertz. Okay, gigahertz. So if it is a frequency is 1 gigahertz, then your time period is 1 by f, 1 by 1 gigahertz, which is 1 by 1 gigahertz is 10 to the power, make 6, 9, 10 to the power 9 hertz, which is like, and we all know what is a hertz. Hertz unit is this. 1 by second. Yes, second, right? So that means this is actually 10 to the power minus 9 second. So if your laptop is running on a 1 gigahertz clock, this means each tick, like each rising tick, the time between them is 10 to the power minus 9 second, which is really small, really small, right? Very small time. And in unit sense, it is called a nanosecond. 10 to the power minus 9 second is called a nanosecond unit. Okay. 10 to the power minus 6 is a microsecond. So modern computer operates with a nanosecond time tick range. This is really fast. Okay. All right. Okay. Any questions so far? Yes, Elias.
Yeah, sorry. You mentioned that like external factors could influence when the ALU gives its result. What happens if it misses that that one clock cycle? Say the result takes too long to compute for whatever reason, and so it's not available in that.
It will result probably a system failure. Hopefully not catastrophic.
Oh, okay, but there's
system,
no.
Yeah, computing system has all this recovery strategy to go through, but it will definitely be a failure if it doesn't compute by that time.
Oh, okay.
Okay, so those factors are all taken care of at the design time, hardware design, and they make sure they actually can fit. They set up the clock cycle, clock speed in such a way that its slowest possible outcome can fit into that time, right?
Okay.
And that's one reason you cannot just bump up the speed like anything. Why cannot you have like 15 gigahertz machine? It's not hardware physically possible because it cannot account for such event.
Okay, thanks.
All right.
Wait, I had another question.
Yes, Vedant.
Yeah, so it's about the ALU. So suppose that the like the operand 1 is 32 bits and operand 2 is 32 bits and the operation is like a multiplication. So how does the output get represented in 32 bits?
That's a very good, interesting question. So multiplication result is always 64-bit. And we'll see when we learn the multiplication, at least at the assembly level, we'll see the result is split up into two 32-bit result.
Okay.
Okay.
Thank you.
No problem. Mengting, I see your hand raised.
Yeah, so I wanted to ask if it was possible for ALUs, for there to be multiple ALUs in one processor.
Yeah, it's possible, always.
If so, like, how would that look like? How would the processor know which ALU to send the information to?
So it's basically, okay. Advanced architecture has multiple ALUs for two different reasons. One reason is a redundancy. Like, let's say you have failure from one ALU, it's basically gone bad. You can look result for the other ALU, right? Especially if you are sending your system onto the space, right? There is no one to fix your ALU there, right? At the space station or somewhere, right? So redundancy, resource redundancy is one reason that multiple ALU can comes into the picture. In that case, your processor will send to the same ALU, like same request to all the ALU, and grab one of the result as long as it is correct, and as long as there is no failure bit up from the ALU. Those are complicated system, redundancy. Another is for hardware pipelining. Hardware pipelining is a concept where you are executing multiple instructions at the same time, purely parallel, like multiple add operation purely parallel. So these multiple add operations from the multiple part of the processor goes connected to the multiple ALUs, but each one part is connected to one ALU. It is not arbitrary that one part can send to another ALU randomly. Okay, straightforward architecture would be one part of the processor sends to one ALU, other part sends to another ALU for parallel instruction parallelism. But I take back my word that yes, we can possibly make another system where your processors, like let's say you have multiple cores, right? Multiple core 1, core 2, core 3, etc. And they want to send to multiple ALU, such ALU, like multiple ALU1, ALU2, ALU3. We can define a bus connectivity with some protocol in it, like network communication protocol, to send requests to any available ALUs. But again, those comes with the complicated hardware cost. Your circuit complication will go up in that case. But yeah, like hardware is a nice field where whatever you want to think, you can implement, simple. However complicated you want to go.
Thank you.
Yes, Ong.
So coming back to the time diagram we are seeing on the slide right now. So you said how when the ALU produces the result within time 1 and time 2, if the result is not picked up as, how do I say, if the result is not being picked up, is it like stored in register file or is it just lying around somewhere?
So it's a good question. So it is really depending on what rest of the system looks like. Mostly it will being stored in a register, like not a register file, but somewhere buffer register. It will be stored for processor to pick it up.
So then after the subsystem pick up the result, it will just destroy it, right?
Yeah, it will be cleared or it will be there for the overriding, something like that.
Thank you.
Okay. All right, if there is no other question, let's move forward. Okay. Here. Now we talked about the memory system model. Again, we started with something like that API interface analogy. And then our interface diagram looks like this, a black box. Let's say it's a 1 kilo memory with read-write control signal with address value of 10 and data of 32, data bit of 32. So it is 1 kilo word of memory, let's say, whatever, right? It has a 2 to the power 10 address values combination. Inside and software implementation can be like that. Hardware implementation, we will talk about that in CS-147 if I teach it next semester. Okay. So we'll talk about the internal implementation of the memory a little bit in that class, but right now let it be black box for you. Okay, how it is implemented. The point here is to understand what is the functionality we are getting. It is not only the logical functionality, also the temporal functionality, as we have explained that wait time, write cycle, etc., in the previous session. Okay, so this topic is all about that. How memory functions from the external viewpoint. Like if you send out the read signal, write signal, some address value, some data, and a clock and a reset, how it behaves. Okay, so these talks all about this thing. Now, from the memory to the register file, we are talking about here what? We are talking about, instead of let's having a bidirectional data, okay, which we already saw, it is a cause of that read-write operation cannot need to wait, right? But register file is internal to the CPU, and it will cost more if we had to wait for that operation. So that's the reason in this register file, we actually split out the out and in so that we can have a back-to-back read-write operation at any point of time. We don't need a wait time there, okay? That is one thing. And also register file is small, like 32, for example. If there are 32 registers, we just need 5-bit of address. We don't need 32-bit of address or 10-bit of address. We just need 5 bits. So that's another difference between memory, which has more bits. 10-bit is at least for 1K, but usually it is both are 32 in the real life. Whereas register file has much less number of address bits. Other than that, it is very basically similar story, logically at least you want to say.
Sorry, what's the advantage of a smaller address?
Small, no, it is not advantage. It is not needed. Like because we are catering 32 register, right? Now you might want to say, hey, why not supplying 1024, 1 kilo register or 2 kilo or 1 gig? So these register files are electronically very different circuit than what memory needs, okay? And these circuits are very costly in terms of area, in terms of money. So more we cannot put indefinite amount of registers in a system. And that's the whole reason we have only few register, but very fast. Okay, so this is slow, this is fast. So technologically, they're different devices and they cost more. That's why it is limited in number in processor. Okay, and that's why this number of address base is also low. All right. So from there, what we want to do is do a little bit more. Okay, instead of one, so here what we are saying that not only back-to-back read and write is possible, but in that case, actually read and write can be possible on the same cycle. Means like read is completed and write is being done on that same cycle on that. And now we want to do 2 read operations in simultaneously. So that's why now we are, instead of having only one address, okay, what we are having is 2 read address, 1 write address, so 5-bit each, okay, and 1 data in and 2 data out. So this configuration gives us to do more parallel operation, like 2 register read at a time. Remember our first day session about how the computer works. There at one point of time, controller was asking register file, hey, give me 2 values from your 2 register, right? This is how, unless we make this hardware, that cannot be possible. So that's why to enable us to do 2 simultaneously read, we have done that, okay? And also, since we are providing separate write address, at the same clock cycle, we can do, processor can request read, at the same time it can request write. Okay, now why this is needed? Let's not answer that question right now. That will be part of 147. Why that is needed? This is more related to the pipelining of the processor, to make the pipeline happens. And pipeline is architecture which makes the throughput, or like it's a faster processor. Let's take it in that way without getting into complication. Okay, but write and read can happen. That request can be sent to the register file at the same time. That is the whole bottom line. Yes, on.
Wait, so if we have like the parallel operation of where you can read two at the same time, it will still take like the same time as how when we only have one read operation, right?
Yeah, each read will take same time, but at the same time point you are done with two read.
Okay.
Okay. Otherwise, what would happen, right? You want to fetch two operands to operate on, right? Let's say two operands for addition. You need to ask one cycle, one operand, another cycle, another operand. So two cycle is gone, right?
So it'll be twice as long, right?
Wasn't?
It will be twice as long, right?
Twice as long. Yeah,
Okay.
exactly. So this will hit your performance. That's why we went with this architecture, because it is small number of storage, and we are inside the processor. So we can actually increase this number of address line. They are 5-bit anyway, right? So with that, we come to the control system model.
Sorry, can you explain again why there aren't two writes? There are two read addresses, but there's only one write address. Why is that?
Because at one point of time, your controller is done with one arithmetic or logic operation that will result in one write. Okay, so usually it is a 132-bit. That's what goes into the register file, except multiplication operation, two register. And we'll see those result doesn't go into the register file. Your processor will have two special register, which will be written together with the 64-bit result. Okay? Other question?
Hi, Professor. I have a question regarding. So is the register file the same as the L1, L2, or L3 cache that we find in CPUs today?
Not really, but what's your name again? I don't see your hand raised.
Oh, my name is Chandramouli Iyer.
Chandramouli.
Yeah.
Chandramouli Iyer. Okay, I got you. I see you. Chandramouli Iyer. Okay, so answer your question. No, register file are much faster than cache. Okay, cache is a complete different abstraction level of storage. Okay, so in this class, we won't consider cache at all. In this class, we'll just assume we have memory, main memory, and we have register file. That's it. That's storage we have in our hand. Okay.
Yeah. So the register file is completely separate from like L2, L3 cache.
Yeah, it's a completely separate story.
Oh, yeah. Okay. So, but both are like used for like temporary, like RAM, like extremely fast memory, right?
Extremely fast memory, but register file are much faster than cache. And cache is much faster than your main memory. So if you look at the speed.
Okay, thank you very much.
We'll talk about cache in the 147 more. Okay, now we have 5 more minutes, most probably, or 3 more minutes. Okay. Now we talked about the control system, right? This is the whole. So we have register file, ALU, memory. Control system is the like ringmaster, the music conductor between synchronizing the operation between them. And these operation we have already kind of went through in the very first lecture, right? That 5-cycle operation. Fetch, decode, execute, memory access, write back. And it just go on and go on and go on like that. That's it. So please refer back to our first day's lecture video. If you are not sure about this module, that will explain that part. Question on this. Nope. All right, then let's take a look what's coming up. Where is my syllabus here?
Should we be able to, I noticed that the problem questions were up. Should we be able to solve all of those now?
Yes, you should be.
Okay. And are they representative of what we would see, for example, on like tests?
Yeah, in the midterm final, yes.
Okay.
Okay, so what is coming up? Oh, number representation. I already told you about that. That's for, yeah, please review it by Monday so that we discuss it on Tuesday. On that part, let's see what is there. This is kind of an easier side of the lecture. Probably it is some, for many of you, it's probably a review of what you know already. So we have like 4 parts telling the different number representation and conversion between them in a generic sense, and then we'll see how to convert from decimal to binary number system, and the decimal to hexadecimal number system, and then how the negative number is represented in a computing system. So that's all we do about that. So we will see like different representation of the number system. Some of the popular, decimal is of course popular, we always use it. Then binary, octal, hexadecimal, etc. And then how we actually write them with respect to base. Like this is, for example, this is 10 in a base of 16, which has a different value than 10 base in 10 versus 10 in octal representation. Same 10 in binary representation is a different value. They look same, but as you change the base, it represents different values simply. For example, 10 in binary system represent value 2 versus 10 in decimal system represent value 10, and 10 in hexadecimal system, let's see, 16, right? 10 represents 16, value 16 in hexadecimal. Now we talked about a general formula of converting a k-base number system into the decimal value. Okay, base k being like 8, 10, 16, 2, 7, 6, 24, whatever you want to propose, right? K is a general base that which represent number of symbols you are going to use in your number system, both base k, and how you can convert into a decimal value of that. The other is the reverse conversion, inverse of that. Like given a decimal number, how you can convert into the base k number system. That's what the general algorithm looks like. And then we'll talk about some of the, apply that algorithm into some of the conversion, decimal to binary, and then binary to decimal the other way, decimal to hex conversion, and hex to decimal conversion. We'll talk about hex to binary, binary to hex, right? And we'll see a shortcut method of doing it instead of going all the way from binary to decimal to hexadecimal. We can straight go from binary to decimal very quickly. We'll talk about that method. And the reverse one of that, of course. Then we talked about the negative number system, especially the concept of 2's complement, very important. Please pay attention to that one. That's it for the next day. Okay, this is all about a little bit on the math side. Question.
Oh yeah, I had a pretty just kind of off topic, I guess, but I just wanted to ask because it's just bothering me a little bit. So is the ALU hard coded with like physical hardware, or does it use like firmware and like minimal like architecture?
It is a physical hardware. We'll talk about, we'll see how we can build a ALU in this class. We'll build one.
Oh, okay.
Okay. And just a sneak peek, like you will see there is nothing arithmetic about in the ALU. It's all about pure logic function. Okay, ALU doesn't do any internally, there is no arithmetic function at all. Everything is logic. And that's why math 42 logic part is very important for you guys to understand. Okay, we'll see that after midterm. I think we'll start building up a ALU. Okay, anything else? We are like 3 minutes overdue of our deadline. Then let's stop tonight.